Good evening, everyone. Thank you for coming today. I'm very excited to be here to present my works with Professor Pham, Professor Huang on this five-based multi-core processor for multi-threading, from a hardware to software design perspective. I will explain our work through a session. We starting with the introduction, which explain our motivation and contribution to parallel computing. Firstly, why is parallel computing important? First, it's address the high performance demand in the post-Moore era, as we can reach the limit of traditional processor scaling predicted by Moore's law. Parallel computing becomes crucial to increase computational power. Second, parallel architecture is now essential for the evolution of computational power. It's not just an option anymore, it's the way forward. Finally, the graphic processing unit or GPU have become a dominant force in the high-performance computing market. Multi or many-core general-purpose processor and customized parallel architecture are also making some impact, especially for tasks that are not easily organized into parallel. However, there are some challenges. Hardware and software development is now developed separately. This separation prevents us from fully exploiting the performance potential of the system. Think of it like having a powerful engine but a transmission that can handle all that power. Because of this disconnect, we cannot fully exploit the ability of the cache, which is crucial for fast data access. Ultimately, we do not achieve the highest efficiency for specific application. As we enter the era of customized computer, the demand for high-performance computing is greater than ever. Companies like Severus are pushing the boundary of Moore's law with their wafer-scale engine, packing trillions of transistors onto a single chip. This graph showcases the exponential growth in transistors over time, highlighting the rapid advancement in parallel computing. Customized computers are indeed a hot topic. A key player in this field is Severus. Their CS3 AI accelerator boosts impressive performance and efficiency compared to most powerful systems like NVIDIA B200. The charts compare the computer capability, power consumption, and performance. In this thesis, I aim to bridge the gap between parallel computer architecture and parallel algorithm. We propose an adaptable framework that integrates both hardware and software design to fully leverage the capability of the hardware platform. This includes introducing tightly coupled accelerator within a multi-core architecture, utilizing the N1 cache and local memory for efficient data-level parallel processing. Additionally, I analyzed and proposed cache-friendly architecture and algorithms that prioritize in-cache processing, minimizing data transfer overhead. This slide provides an overview of the thesis structure. Chapter 1 to 3 cover the introduction, background, and literature review on the parallel computing, RISC-V, ISA, and multi-threading. Chapter 4 details the design of the proposed RISC-V multi-core multi-thread system and its accelerator. Chapter 5 and 6 present the concurrency programming flow with cache adaptive strategy and illustrate the application of the multi-core system. Finally, Chapter 7 and 8 discuss the results, comparison with recent work, conclusion, and future research direction, including security consideration for the proposed multi-core system. In this session, I will clarify the background research of this work. To begin, let's discuss the foundation of my research, RISC-V. RISC-V is an open source instruction set architecture that offers flexibility for both hardware and software development. It's completely free and accessible, defining both hardware architecture and compiler requirements. RISC-V modularity and customization make it suitable for various applications, from high-performance computing to low-power embedded systems. Developed to overcome limitations of existing ISA, RISC-V is revolutionizing the market and research. For hardware design, I utilize Chisel, a hardware construction language embedded in Scala. Chisel facilitates hardware design through object-oriented and functional programming. It connects to low-level hardware description language through FARLTL, which performs transformation and optimization. This streamlined process allows for efficient hardware design and implementation. Now let's summarize existing parallel hardware system. ASIC are custom designed chip for specific application, offering high efficiency in computational power. GPU originally designed for rapid rendering, has evolved into massive parallel processor, dominating high-performance computing. FPGA with their configurable logic block offer flexibility for various applications, although they consume more power than ASIC. Finally, hybrid many-core processors combine identical and specialized cores to boost energy efficiency, accelerating compute-intensive operations without excessive energy consumption. Multi-thread programming is crucial for leverage parallel computer architecture. While it allows us to utilize multiple cores, it also introduces complexity with shared resources. Achieving high parallelism and scalability on large multi-core systems remains challenging, especially with load balancing and data management in accelerator-based platforms. Programming strategy and tools like OpenMP and Intel Training Building Block aim to address the challenge and enhance programmability and portability. Finally, let's consider on caching strategy and security issue in multi-core systems. Caching algorithms such as least recently used are essential for efficient data management. However, multi-core caching presents challenges due to non-determinism and varying response time. On the security aspect, trust execution environment provide a secure space within the processor to protect critical assets. TE ensure confidentiality, integrity, and availability of sensitive data and operation, mitigating physical and side-channel attacks through hardware-level security feature. Now, let's dive into the literature review. This slide provides a visual presentation of the research landscape, highlighting key areas relevant to my thesis. The central theme on this work lies at the intersection of several key research domains, from parallel algorithm, multi-core architecture, to cache-friendly strategy, single-instruction multiple data processing, many-core system, threat model, and trust execution environment. Cache friendliness is essential for optimizing multi-core systems by enhancing performance through efficient data access patterns. We can minimizing data transfer overhead and maximize cache utilization. The successful of design cache-friendly algorithm depend on the understanding of data locality, which includes spatial locality and temporal locality. Research insights such as this asset machine model emphasize the importance of temporal locality for using data. The strategy like processing data input and processing data as it arrives promotes data storage close to the processor for improved access efficiency. Modern multi-core processors typically feature a cache hierarchy, multiple core and vector units. For instance, the Amazon C5 Metal instance boasts a 48 physical core with hyper-threading, resulting in 96 virtual core operating at 3.4 GHz. The cache hierarchy includes private N1 and N2 cache for each core, along with shared N3 cache. RISC-V implementation for multi-core CPU include ARA, an energy-efficient vector processor, or Sparkle, a many-core architecture based on the RISC-V 32. Security is a critical concept in multi-core systems. Evasion of attack exploit parallel execution capability, make it detection difficult. Malware can distribute operation across core, camouflage malicious activity, and manipulate shared resources. Concurrency spy attacks such as recondition, atomicity violation, top 2 attack, and deadlock attack can also compromise system security. Optimizing parallelism and cache friendliness is challenged due to the memory hierarchy and bottleneck. Cache-friendly algorithms require understanding complex and often private system architecture. Integrating cache-friendly and parallel algorithms is complex, and concurrent access to the same data area work cache organization is nearly impossible. To deal with the challenge, RISC-V ASA offers a potential solution, which is open ASA, compiler toolchain, and well-defined software-hardware communication, facilitating customization for optimizing multi-core systems. In this session, I will present our proposed hardware architecture for multi-core multi-thread support system. In this session, I will present our proposed hardware architecture for multi-core multi-thread support system. The core of our design is a RISC-V system featuring a file-state pipeline, instruction fetch, decode, execute, and memory access and write back. The cache subsystem supports highly interconnect with MESI-like protocol, ensure efficient data management. In addition, the proposed cache architecture allows high bandwidth low overhead data exchange with tightly coupled accelerator, which are a feature of the RISC-V. A key element of our design is the tightly coupled accelerator support system, which allows the accelerator can from different private internal RISC-V results, such as the register file, execution unit, and even data cache. The generated results are able to write them back to the register file and data cache, ensuring efficient data processing and sharing between RISC-V core and accelerator. Synchronization with the RISC-V core is achieved through an interrupt and done signal. The interrupt signal forces RISC-V core to process the feedback from accelerator immediately, while the done signal allows RISC-V to decide the time that accelerator response is processed. To further enhance performance, we introduced high bandwidth private bus between the RISC-V core and tightly coupled memory. This private non-interrupt bus supports both typical width, which is 32 or 64 bits through register file or execution unit, or high width bus through high bandwidth interface of the cache, facilitating rapid data transfer. The cache is a cache port. It plays a role as unified private data memory between RISC-V core and accelerator. Our suggested cache design allows the cache to be used in different scenarios. A near core private memory, a shared memory between the core and tightly coupled accelerator, a buffer for accelerator, and a buffer for core-to-core data exchange, which optimize data handling and communication. The interleaving cache architecture distributed data across multiple memory banks, enabling simultaneously access to different memory locations. This approach enhances bandwidth and reduces latency during data retrieval. In our suggested unified private cache architecture, the interleaved organization is taken advantage to extend the bandwidth of the memory interface, which is the core idea of high bandwidth interface. This way, multiple cache banks are compiled to provide a wider bus width. Based on the high bandwidth cache architecture, we propose the core-to-core tunnel, which performs bottleneck in multi-core system by managing communication between cores. Data is transferring directly between cache, reducing reliance of the shared bus and improve overall system efficiency. In this scenario, the software will allocate a region of the cache to be used as a buffer to transfer data from cache to cache. In our proposed RISC-V architecture, the operation of the RISC-V core are affected by the tightly coupled accelerator and core-to-core tunnel. It makes more difficult for traditional pipeline model to ease such issue, we suggest a function target model, which abstract different parts of the system depending on the function or characteristic. We divide the system into four parts. The front end that takes care of instruction fetch. The core generate control signal and decide when the control signal are dispatched. The back end takes care of basic operation and write back results. And highly coupled accelerator focus on accelerator design. The four parts could be developed separately and can be customized to adapt to different architecture or target application. But they must follow a predefined communication protocol to synchronize with each other. The multi-core system comprises four asymmetric core for efficient parallel processing and resource utilization. Each core has a private N1 cache, a shared N2 cache that facilitates inter-core data exchange, and a thread queue that supports multiple thread management. The system architecture includes a memory bus for core-to-core memory communication and a peripheral bus for I/O device connectivity. Coherent Manager maintains cache coherency, ensuring data consistency across core and cache. The N1 cache acts as the private, high-speed memory for each core. The tiling protocol manages coherence between N1 cache, preventing stored data. Each core N1 cache connects to the shared N2 cache. The N2 cache is designed to facilitate the operation of highly coupled accelerator and near cache processing as I mentioned before. Core-to-core communication utilizes point-to-point communication with data transferred directly between cache. Allow overhead protocol with request response and synchronization ID ensure efficient data and reliable data exchange. A core-to-core exchange operation is driven by a couple of software instructions from source and destination core, with a send and receive command. The two command is synchronized with each other by using the same ID. So when the sender and the receiver write the corresponding instruction, the sender will send a request with the synchronous ID to the receiver. So when the at the same time receiver waiting for the request from the sender, and they check the receiving ID. If the sync ID is matched, they will set the response signal. At the same time, the sender is waiting for the response signal, and then when they receive the response signal, they begin sending data with the valid signal. So when all the data have already transmitted, and the sender will rise the will reset the request signal, and when at this time the receiver check that the request signal is reset, they will reset the corresponding response signal, and then and return the feedback for the call to continue the next instruction. The quarter node is work at the tightly coupled accelerator. Therefore, the send and receiver command can be processed at the blocking or non-blocking operation, which means the call could be wait for data transfer or continue with the next operation that not require the transferring data. The trash management system employs hardware-software co-design approach. A shared trash queue manages task distribution among core, optimizing performance and reducing idle time. The trash manager includes the FIFO to receive the generate trash from the main core and distribute it to the corresponding FIFO if indicates. Otherwise, the surprise thread is distributed to the destination FIFO depending on the balance strategy. Keystone, an open source framework, provides a secure multi-threading by isolate enclave memory, managing thread execution within the enclave and preventing OS control over enclave page table thread execution. Keystone relies on the root of trust to ensure the integrity and security of its trust execution environment. Firstly, our suggested isolate subsystem provides the root of trust. The secure boot process starts with the isolate subsystem booting first with the secure bootloader or SBL in the isolate boot ROM. Next, the zero-state bootloader is copied from object to the isolate subsystem RAM. The zero-state bootloader or ZSBL is then hashed and combined with the signature and stored public key in isolate flash memory to verify its integrity. Finally, a true random number generator generates a sys to create a key pair, which are then used in Keystone. The tightly coupled accelerator connects directly to the RISC-V core, fetching data from the cache and writing result back to the cache. Our proposed design leverages the high bandwidth interface of the cache to improve performance. We propose three tightly coupled accelerator architecture, which is supported by our proposed multi-core unified private cache architecture. The matrix processing unit or MPU utilizes cyclic array for parallel matrix operation processing. Its processing element perform arithmetic and logic operation, tightly coupled to the RISC-V core and controlled by custom instruction. The MPU maximizes performance for matrix-related applications. This design accelerates linear algebra computation by utilizing the full capability of the first system. The Puro-Wheeler align short DNA sequence against a reference genome. The tightly coupled accelerator focuses on speeding up the sys extension phase of the alignment algorithm. Controlled by custom instruction, it interacts efficiently with the RISC-V core. The BWI architecture is designed for parallel processing. The proposed design is able to scale up to exhaust the bandwidth of the user bus. Finally, the Thesis accelerator employs a parallel matching algorithm for efficient test retrieval. It is optimized for handling large datasets, enabling rapid searching. This accelerator achieves higher throughput than traditional search algorithms, making it suitable for application requirements with access to large volume of test data. The performance of the bandwidth of the memory limit this architecture. It could easily scale up the number of processing elements to exhaust the bandwidth of the memory. Not only our proposed accelerator, but almost all parallel architecture is limited by the bandwidth of the memory system. Our proposed architecture can satisfy this requirement by providing large width, low overheads, and scalable internal memory system. When compared with the accelerator, the general-purpose processors are less efficient in terms of performance but are more flexible by allowing programmers to redefine the control flow of data by software. In this work, we provide a hardware architecture that combines both advantages of general-purpose processor and accelerator, but to maximize the benefit of our proposal, so it requires an appropriate programming model, which I present in this session. Let's explore the proposed software strategy for multi-core, multi-thread computing system. This strategy aims to optimize performance and resource utilization. The core of our proposed strategy is cache adaptive algorithm and hardware-software co-design. Cache adaptive algorithm adjusts to dynamic memory usage pattern, enhancing overall system effectiveness. The hardware-software co-design approach enhances thread management by integrating hardware and software functionality, maximizing parallelism and efficiency across multiple core and highly coupled accelerators. Cache adaptive algorithms play a crucial role in optimizing performance in multi-core systems. They adjust to dynamic memory usage, improving data locality for efficient memory access, temporal locality where program revisit recently used data, and spatial locality where program access physically close data are key aspects of the algorithm. In dynamic memory environment, algorithm need to adapt as cache size changes. The multi-thread control mechanism implements in firmware. The primary core creates a thread using the thread create method, which supplies the thread function address to the thread manager, passing necessary data and its address. The core then checks their file for thread availability. If it's empty, they return to sleep mode, ensuring energy efficient while waiting for tasks. Once a thread is available, the core saves its current state, fetch the thread information, set the stack pointer to the private cache, and execute the thread function, restoring its state afterward. By setting the stack pointer to the addressable cache memory, the compiler moves the activation table of the task to the local cache of each core. They allow data to be processed near the core and can be fetched by tightly coupled accelerator without overhead. In this strategy, the critical condition is that the processed data must be small enough. This is how the cache additive approach becomes crucial. The hardware-software co-design also allows for dynamic thread management. Core wake up to perform tasks from a shared thread queue, maximizing resource utilizing and parallelism. The thread distribution strategy could be performed by hardware or redefined by software. The unified cache control mechanism optimizes data access. The thread stack is allocated within the private cache of the core running the thread by setting the stack pointer. Local variables are also stored in the private cache for fast access. To work with data from shared memory, the thread copy data to local variable within each private cache, minimizing access to the slower shared memory during computation. When the thread needs to utilize the accelerator, it sends command and data to the accelerator. The accelerator fetch input data from the private cache through the high bandwidth cache interface and write back the result to the allocated memory. Once the accelerator is done, the results are typically stored in the thread private cache, and the thread then write them back to make them accessible to all the thread or the main program. The secure boot process starts with key generation. The manufacturer generates a pair of root keys using RSA cryptography. The private key is kept secure offline, forming the foundation of the security scheme. A trust third party generates the root key responsible for certifying the device identity, and a certificate is issued for the device, binding its identity to the roots of trust. The boot process starts with the device executing code from its read-only memory or ROM. The initial bootloader performs basic hardware initialization. The bootloader then loads and verifies the next state, which is responsible for loading the operating system kernel. This verification ensures that only trusted software executes. Now I move to discuss the deploy application to illustrate how our hardware-software co-design system work. The target application include matrix multiplication with subtraction algorithm and divide conquer strategy. The matrix multiplication problem are deployed through four steps. In the tiling step, it optimize the access pattern. In the data prefetching step, it prefetch the prefetch data to reduce the latency. In the loop reordering step, the to increase the cache efficiency, and finally in the adaptive step, dynamically tune algorithm parameter based on the underlying hardware and workload characteristics to improve performance. The matrix multiplication with the divide and conquer strategy. We assume two input matrices A and B. The output matrix C is calculated as shown in this slide. It involves A multiplication and 4 addition. The data flow of matrix multiplication is right here, showing the steps involved in fetching and processing the matrix. The order of the calculation is modified to take advantage from core to kernel and to minimizing the space requirement for temporal results. Firstly, uh, the data from the first matrix are fetched into the private cache. Then the related part of the matrix B is fetched into the uh, private cache and perform the multiplication into the submatrix. Then the results are then stored in the private cache. But these temporal results are not writing back to the shared memory. It will transfer from the core 1 to core 0, from the core 3 to core 2 to core kernel. And then when the final result are calculated, it then write back to the shared memory. So this step repeat from step 5 to step 8 to calculate the rest of the matrix results. The output matrix C using traction algorithm is calculated as shows. This algorithm reduce the number of multiplication but increase the data exchange through the shared bus and temporary and requirement space to store the temporal variable. Therefore, it's not appropriate for our proposed system. We rely on sketch with limited memory. We will prove it through experimental result in the next session. The 2D convolution using splitting method include four steps: initialization, applying filter, data exchange, and output generation. In the initialization step, it call fetch its filter into its private cache and load a portion of the input image from shared memory. In the applying filter, it's called apply it assign filter to its image portion, calculating output pixel based on the filter. In the test step 3, with the data exchange, after applying filter call exchange result with neighboring call to ensure pixel computation accuracy. And finally, output generation. The final result from on call are compiled to form the complete input image and then write back to the shared memory. The data flow of 2D convolution is right here, showing the step involving in fetching, filtering, and generating an output image. Uh, Firstly, the filter kernel are fetched into the private cache of each core and keep it until the end. When begin filter, the corresponding value of the input image are then fetched to each core, and each core will be used the corresponding filter kernel to process the input data. Then the output image will then write back to the share share memory, and then this step is repeat until all the input pixel are processed. The CRC32 algorithm with duplicate kernel involves initialization, pre-computation of a lookup table, and iterative calculation through the input message. At the first step with a initialization, the CRC32 algorithm initialize a CRC value typical set to on F. Then in the step 2 is the pre-compute. A pre-compute lookup table of size 256 is created for fast access to CRC value corresponding to all possible byte value. And the final step is iterative calculation. The algorithm iterates through each byte of the input message, combining it with the current CRC value and using logical operation. The data flow of CRC32 illustrated here show the steps involved in fetching data from the recompute lookup table and calculating the CRC32 results. The main idea is similar to the 2D convolution process, but because of the input messages cannot be split at the image, different kernels are distributed to different cores to process different input messages. In this session, I will review the performance of our proposed software-hardware multi-core multi-thread system and compare it with other work. The comparison includes comparison with the other proposal without accelerator and existing one with accelerator. The comparison shows the performance of our proposed multi-core multi-thread system and how effectively our system can support the accelerator. For performance analysis, I utilized the Xilinx VCU 118 evolution kit built around the Vertex UltraScale uh, FPGA. The kit includes a peripheral module interface for easy connection to various peripheral and external memory. The Xilinx Vivalo design suite 224.1 were used for design synthesis. The proposed RISC-V-based multi-core system with a 4-core configuration was fabricated on Rome 180 nanometer technology. The Antera FPGA-based platform TR4 was used for testing the chip, serving as a power source, external memory, logic analyzer, and level shifter. This table presents the resource analysis for both 4-core and 8-core systems, showing the utilization of NUT and resistor. The frequency achieved in the FPGA implement is also provided. So from this table, you can see that the track manager system only costs 0.26% of the total NUT usage of the whole system in both 4-core and 8-core conversion, and the design the cache manager for the high bandwidth memory for the addressable cache it only increase 6.42% of the total NUT usage of a single RISC-V core. This table shows the CMOS 180 nanometer synthesis result, including standard cell area, and one cache size, the track queue size, frequency, power consumption for both 4-core and 8-core configuration. Because all more resource is consumed by the RISC-V core, when it reaches the number of core by 2, the number of standard cell and also the cell area also increase nearly twice. This is the layout of the 4 chip with the size 4000 with the size 4500 multiplied by 3400 millimeter square and with the density of 78%. So the core are layout with the 4 core. Each core has a private E cache and the D cache with the local arbitrator and the RISC-V core and connect the 4 core is connect with the bus system, and the bus system is also connect the FPU and the internal SRAM including the N2 and the internal RAM. This table and graph show the maximum frequency and power consumption at different VDD value. The minimum working VDD is 0.9 volt. At 0.9 volt, the system can work up to 10 MHz. When operating above 1.8 volt, the system can work up to 73 MHz in reality. The power consumption is changed from 50 MW at 0.9 volt up to 416 milliwatt at 2 volt. This table and graph present the power consumption at 10 MHz for different VDD value, including active power, P active, the ideal power or P ideal, and sleep power or P sleep. The P active is measured when the system is work, when the P ideal is measured when the system is in the reset state, and the P sleep is measured when the clocks is not provide. The table and chart reveal the power consumption when the system is working at maximum frequency, which is 73 MHz. At maximum frequency, the system can only work when the input VDD is higher than 1.8 volt, which is also the recommended VDD of the room 180 nanometer technology. So you can see that at 2 volt, the maximum maximum power consumption when the core works is 416.64 milliwatt. This table presents the performance result for matrix multiplication using the iterative method, showing the number of circle per instruction, and speedup for different matrix dimension and core count. The speedup achieved 3.68 times with 4 core and more than 8 times with 8 core. The statistic divide and conquer strategy promote performance by maximizing the usage of private cache and reducing sharing of usage, especially share memory and share bus. The speedup achieved more than 5.5 times with 4 core and 8 up to 18.6 times with 8 core. Besides reducing sharing of usage, the proposed order also promotes bus transfer on the bus, then significantly reduce the overhead of data exchange. With 2D convolution node, the proposed system and strategy reduce the data exchange by keeping the filter kernel inside the cache and avoiding inefficient cache replacement. In this way, the system achieves the speedup nearly 4 times with 4 core and nearly 7.2 times with 8 core. With CRC32, the initial table is kept inside the cache, and only the message is fetched and replaced. In this way, the proposed system can avoid inefficient cache replacement and improve performance. The speedup achieved 4.8 times with 4 core and 9.28 times with 8 core. Divide and divide and conquer strategy with the modified order show a speedup from 4% to 16% by reducing the cache requirements and take advantage from core to quarter node to reduce share bus usage. This table shows the comparison with other work in matrix multiplication. On the compared system do not use accelerator. The results show our proposed system achieves significantly higher speedup per core when compared with other work. Even with narrower bus width, the reason is that our system takes advantage from the near core processing by using cache as memory and reduce the conflict when using the share bus. This table compares the execution time of PWA6 extension using multi-threading and tightly coupled accelerator for different query length and target length input string. The BDPlay accelerator always consumes significantly fewer circles than the multi-core system, even with a core conversion. It proves that the accelerator is an efficient solution for data parallelism in almost specific applications. This table shows the speedup of the BDPlay MEM accelerator over multi-core multi-thread system. The speedup can achieve nearly 600 times when compared with a core and more than 4,000 times when compared with one core. With the Thesis problem, the speedup is only achieved from 1 to 5 times. The Thesis accelerator is less than efficient because state matching is a simple task that could be performed in a single circle by the robot processor. In addition, this problem is greatly affected by the bus width. The experiment showed that not all problems can be effectively processed in parallel, especially the problem that cannot be performed in parallel like CRC32 or Fibonacci. But even in the case our proposed multi-genre but cores with core processing can still provide an effective solution. This table shows the performance of the matrix processing unit with the unified cache support in terms of execution time. This table reviews the speedup of matrix processing unit over the multi-core system. The matrix processing unit can achieve a speedup to 140 times when compared with a single core and around 18 times when compared with a core. The size of the MBU is scaled with the bus width that the unified cache could provide. It avoids the matrix processing unit need to store to wait for data and then efficiently use the energy. Then finally, we compare our system with matrix processing unit with another system with the corresponding accelerator. We deploy our system with three scenarios: single core with narrow burst, single core with wide burst, and multiple core. The results show that a single core with wide burst provides the best efficiency. It's proved that the bottleneck in memory is the weak point of almost intensive parallel system. Therefore, our system provides significantly higher efficiency when compared with the other RISC-V system uh, by promoting in-cache processing and intelli-cache architecture to promote higher memory bandwidth. Finally, I will conclude our work and suggest the next plan for this work. This dissertation proposed a RISC-V-based multi-core, multi-thread system to address the increasing demand for parallel processing. It demonstrated a concurrency programming flow leverage the RISC-V architecture, including techniques like divide and conquer for optimizing algorithm performance in various memory access scenarios. Performance analysis shows significant pickup compared to single-core implementation, with promising results for resource consumption and minimal overhead in multi-threading support. The fabricate four-core chip with ROM 180 nanometer technology is able to work up to 73 MHz. There are some limitations that could be improved in the future. Firstly, the static track management scheme, while efficient for specific architecture and workload, lack adaptability to changing conditions over device tasks. In the future, uh, we should explore the dynamic track management for enhancing efficiency and using more efficient in power. Secondly, the current design do not explore power-aware optimization. Future improvement include developing task allocation strategy that consider power consumption characteristics. Finally, a robust verification system is essential for ensuring accuracy in hardware design. Despite using multiple tools, a runtime verification framework is necessary to enhance debugging and ensure design specifications are met. After improving the limitation, we will target a many-core system, many-core processor featuring 10 of 100 core on single chip, are driven by demand in data-intensive application, artificial intelligence, and high-performance computing. They promise unprecedented performance by enabling parallel task execution. There are four elements that need to be considered when designing a medical system. Firstly, is the network topology. Mesh and torus topology are scalable network topology for interconnecting core. Hierarchical network combine multiple network levels to reduce latency for frequent communication. Next is the programming model. Uh, the current task space and data flow programming model allow efficient parallelization on many core systems. A hybrid programming model will bring more efficient to maximize the performance of the many core system. Next is the security of the many core system. There have been in the recent year there have been a lot of research uh, over side channel attack that can exploit conditional or thermal vulnerability to leak information or disrupt traffic to collect the sensitive data. So on the such on the security aspect need it also need to um, receive more attention when we consider to design a medical system. The many core system in the future work in low hierarchical interconnect that combine high bandwidth and low latency for nearby core with a scalable network for distant core. A hybrid programming model combines task space and data flow programming model will allow developers to express parallelism at power level. Security will be integrated through hardware feature like memory protection unit, secure enclave, and secure inter-core communication. The system will include a comprehensive software stack with compiler, runtime system, and debugging tool. Thank you for this listening. So next, I will show the demo video and explain how our fabricate chip work in reality.